Hello students, now welcome to this second episode on breadth first search. As you have seen in the introductory lecture, you just got an idea that what breadth first search is. Believe me, I have seen students who have taken a formal course of algorithm and data structures in their BTech or undergraduate degree, and if you'll ask them after 1 or 2 years that what breadth first search is, they have no idea. So at least after watching that 8-minute long video, you are better than those students. Anyways, now let's continue with our formal discussion. Not continue, in fact, let's start with our very formal discussion on how we're gonna use breadth first search, how we're gonna implement it using data structures. So let me take the same example which I had taken in the previous lecture. Now suppose if there is a real life practical problem of running a breadth first search onto a graph, definitely you're not going to make a spherical wavefront. And secondly, how you're going to implement it in the language of computers, that is through programming languages, right? So now let's discuss that. So as we have seen, there are two graph traversal algorithms, depth first search and breadth first search. In depth first search, the basic data structure through which we implemented it was stack. In this case, it will be queue. So next, a very important point you must keep in mind that breadth first search is implemented using queue. Now, once you remember that, then there is absolutely nothing more you need to remember throughout your life. You remember it is implemented through queue, and that's it. Now you can run BFS on any graph. How? Let's see. So for example, let me make a queue, correct? And definitely this is the front of the queue and this is the end. And in queue data structure, how it works, you know it very well, just like a normal practical day-to-day queue. Once who enters first, leaves first, gets service first, right? So how do we implement it using a queue? It's a very simple case, very simple concept. So let us see that. Let us see that. Let us assume that A is our start node. Now what you do? Take this A node, put it into the queue. So I've put A, correct? Done. Now, next step, take this A out of the queue. Definitely, since this is the only element in the queue, anything now you want to dequeue or anything you want to take out of the queue will be A. Okay. Now I have taken A out of the queue. Now what I do? Having taken A out, I'll see its neighbors. Its neighbor means in the graph to which other node it is connected. So it is connected to B and C. Now what I'll do? I'll insert this B and C into this queue. B and C. Now the order could be any, could be different. You could have inserted C first and then B, just like we did in the stacks in DFS. Order can be anything, and that's why there is not a unique BFS traversal of a graph. There can be many variations. So in this case, we have pushed B and C, all the neighbors of A, into the queue. Now what? We have done that, pushed all the neighbors of A. Now again we will dequeue the queue. So what we'll get? We'll get B. Now see all the neighbors of B. What are they? D and E. Then push D and E into the queue. Correct? Now, definitely, now you have to DQ operation you have to perform. What you will DQ? C, correct? C is now taken out of the Q. And now see what are the neighbors of C, F and G. Push F and G into this Q. Again, order is not relevant, but since we have taken one particular order, so we'll go by that only. Now what? You have pushed these elements. Now turn off, taking out something from Q. What will come? D will come, right? Then, are there any neighbors of D? No. Now here, one thing I would like to mention you, I should have told you earlier also, as soon as you NQ something, so then what you will do, since you have NQ'd A, you will mark this A as visited, right? So it has been visited, right? So let me mark this with a green one. So once you have NQ'd A, you should have marked it as visited. Then you should have marked B as visited and C as visited. Why? It is so because when you are at B, now you will see the neighbors of B. Now you could have said, sir, not only D and E, but A is also neighbor of B. So at that time, why you didn't push again A into the Q? Why didn't we push? Because A was already visited, right? Similarly, once we have pushed D and E, we'll mark them as visited. Same for F and G and for C as well. Now, let's come back to where we left. We'll take D out. See, are there any neighbors of D which are not visited? So my statement has to be slightly modified, which has not been visited. B is a neighbor, it has already been visited, so there is nothing to explore. Fine. Next, then we'll take E out. Same case, are there any neighbors of E which are not visited? No. Take F out. Are there any nodes of F? No. Then it's turn of G. Are there any nodes, any neighbors of G which has not been visited? No, there's only one neighbor C and it has already been visited, correct? So what would have been order here? So after D, you have taken out E and then you have taken out F and then you have taken out G, correct? So let me write it again here. So what has been the order? Again, this was the order, right? So this is nothing but your BFS traversal of this graph. So BFS traversal is nothing but A, B, C, D, E, F, G. A, B, C, D, E, F, G. Is it clear? So this is how we have performed BFS using a very simple data structure, which is our Q. I again repeat what I did. Just first of all, I pushed A into the Q. Second time, it was the time of taking something out. Since A was the only element, I took A out. Then mark it A as visited. I had already marked it visited when I pushed it into the Q. Then take A out. See what are the unvisited neighbors of A, B and C. Push them into the Q. Then you have to take something out of the Q. Which node will come? Definitely B. It's a Q. B will come out. See what are the neighbors of B which are not visited? D and E. Mark D and E as visited. Push them into the Q. Then this turn of C. Take C out. See what are the neighbors which has not been visited? F and G. Mark them as visited. Push them into the Q. After that, you come to D. There's nothing to explore. Pop D out. Then E. E will also come out. Similarly, F and G. Right? Now, after this, I'll take one more graph for you to practice. And with this, the concept that how BFS is implemented using Q is done. So students, now let's practice BFS traversal on some graphs. So Now you know the basic concept. The basic concept is very simple. So let's practice it out. And this time we'll go with some speed. Now, okay. So let's take this example. So in this graph, B is my starting node. From B, I have to start the BFS traversal. Okay. So now, as per the algorithm which we saw in detail in the previous lecture, how will we proceed? First of all, we'll push B into the queue, right? Now, and mark it also as visited. Now what we need to do? We need to pull something out, DQ from Q. So what element we can DQ? Only B. B we have taken out. Now see the neighbors of B which have not been yet visited. So what they are? A and C. So I'll push A and C into the Q and also simultaneously mark them as visited. Now what? Now which element should I DQ? This is a Q data structure. So I have to proceed from the front. So I'll take A out. Fine. Now I've taken A out and I'm also marking it, the visited, like this, right? So now A is out. So what are the nodes, neighbors of A which have not yet been visited? Definitely only one, that is D. So I'll push D into the Q. Now which element should I take out? C, correct? Now again D, once we push D into the queue, we'll mark it as visited. So when we have taken C out, what are the neighbors of C which has not been yet visited? Definitely there is only one neighbor, F. So F will push that into the queue and simultaneously mark it as visited and push it into the queue. Now what we need to take out? D. Again the same logic. What are the neighbors of D which has yet not been visited? Only one, that is E. So we'll push E into the queue and mark it as visited. Fine. Now what? Now E, now what do we need to take out? Definitely F. So any other neighbor of F which has not been visited? Yes, there is only one neighbor which has still not been visited. G, will mark it visited and push it into the queue. Now what? E is remaining. We'll take E out and then see any neighbor of E which has not been visited? No, nothing to do. Proceed to further. Then we'll take G out. Any neighbor of G which has not been visited? No. And we'll take G out and there is nothing to push into the queue, and also there is, now queue is empty. So algorithm has terminated, right? So finally, so this basically this sequence, if somebody asks you what is the sequence of the BFS traversal, the sequence of visiting node when you are running BFS algorithm, so what it will be? Definitely it will be this only: B, A, C, D, F, E and G. And you can also see here, see, is it not going breadth wise, the same approach which I told you earlier? So if you see from B, which are the two nodes which got visited? B is your center, A and C. Then next level is D and F, and finally you can see E and G, right? But this is the method, this is the algorithm you run using Q, right? So now next graph we'll take will be a directed graph. So this is an undirected graph, right? So I hope you know what is the difference between directed and undirected graph. So suppose there are two nodes. Now this is a directed graph. So you can go from A to B as well as from B to A. But if I put an arrow like this, so it means there is only one way path, only A to B, or I could have made it like this also. Then it would have mean only from B to A. You cannot go from A to B, right? So now we'll see how to run BFS on a directed graph. Concept will be almost same, only one small minor modification you have to do in the algorithm. Rest will be same.